All right, here we go.
Nice.
Checking OBS, looks pristine. All right. All right, here we go. So this is continuing on the history of interferometry. This is covering a series of experiments that was done in 1940 to 1942, continuing the Sagnac experiments of 1913. So if we remember back to the rotating turntable with a light beam and detector fixed to the turntable, as they rotate together, it produces a fringe shift pattern that is proportional to the velocity of the rotating turntable. All right, that's for the thumbnail thing. So this is a diagram of what we're going to be looking at here. So imagine that this top part here, imagine we're like looking through the top turntable here, but there's a top turntable here that has 45-degree angled mirrors on it. This turntable, the top portion is stationary. Now on the lab, against the wall is the laser beam, so the source emitter, and also a detector. Now this is going to be important for distinguishing, the distinction between what relativity predicts versus the classic theory in regards to reference frames and the relevance of that, which we'll get into specifically why they did this configuration. But to continue on with what they did here, so just to remember though,
does the light hit where your blue dot is? The light comes in there.
Yeah, so the source emitter and detector would be on H fixed to the lab wall. It would be sending a light beam to this mirror here, or a beam splitter here, and then it's going to split the beam going clockwise and counterclockwise. And then when it hits the 45-degree mirrors, it hits the bottom turntable that has 45-degree angled mirrors that send it around a loop on the turntable, which rotates. And then when these line back up, the 45-degree angled mirrors send the beam back clockwise and counterclockwise, like it would as if it was on a 2D plane.
Wow, very cool.
Dude, extremely cool, right? So it takes the 2D plane of the Sagnac effect and extends it into 3 dimensions here. So this is next level.
That's
really.
awesome. Yeah,
it's nuts. It's nuts when you think about it. And then so additionally, there's also a way where the beam gets split and it hits a detector that is fixed to this rim of the rotating apparatus as well. So there's 2 detectors that can be utilized here, one fixed to the lab wall, one fixed to the rotating turntable, and the source emitter is fixed to the lab wall, of course. And then they obviously did a configuration where the source emitter was fixed to the turntable as well versus everything else. So they did like one of each possible configuration.
That's awesome.
All right, so here's the lowest quality image I could find on Google to show you guys the representation of this landmark experiment here. But this is what we're working with. So we can see this top portion here is fixed. Now the distance between here for the separation in regards to this, what this distance would be, is about 4 centimeters. So this is extremely close. Now the turntable, the bottom portion here rotates. So this is what's going to be rotating. And then of course on the lab wall somewhere here is a detector and a laser. All right. So here's another look at the path of light that it's going to take, as I kind of went over earlier. The turntable is going to be turning clockwise, and the beam is going to be coming in here from the top portion, split clockwise and counterclockwise to itself, and then it's going to hit these 45-degree angled mirrors where it's going to hit more reflectors, complete a circuit on the rotating turntable, and then also return back to the 45-degree angled mirrors. And then as this rotates, when these when these 45-degree angled mirrors intersect, that's going to send the light beam back to complete its circuit. And then they're going to be, and then like the chunks that come back in phase, or the chunks that make it, when they intersect, is going to, they're going to be able to take the phase difference of that and determine if the velocity of the turntable is translating to the observer fixed to the lab wall, which in the current paradigm would make no sense. It would be impossible, because a lot of what's put in contention for relativity theory to explain the Sagnac effect, Zach, you're kind of hot micing, it's all good. A lot of what's put forward to explain the Sagnac effect is saying that, oh, well, if the detector if the detector is fixed to the turntable, then because it's rotating, it's a non-inertial observer because a rotation is an acceleration. So we'll get in. So this is why they did these explicit configurations here to show that an inertial observer, even fixed to the lab wall, you can't get any more stationary than fixed to the lab wall. So if that doesn't count as an inertial observer, then what are we doing here, right? So this is a direct refutation to the mainstream paradigm. Now, why is this important? Because all technology, all current mainstream technology accounts for the Sagnac effect when it comes to inertial navigation systems, GPS, any interferometry experiment. So like Michelson-Morley, the Sagnac experiment. Any time they talk about, hey, we're measuring Earth rotation, they're not measuring Earth rotation. They're measuring the fluctuation in the speed of light throughout the day, and that when you plot the minimum and maximum dimensions of that throughout the day with respect to sidereal time, so a timeline that's 23 hours, 56 minutes, it makes a sine wave. So they've never measured a ball rotating. They've measured a timeline that corresponds to the stars. And in addition to that, if you want to get real technical, when you add Dayton Miller's work to it, they measured the position of the stars and the sun throughout the year, which is what the measurements really show. But anyway, that's what's being measured here, and this is all dating back to being derived from the 1800s, where they figured out how they could take these precise measurements, which we went over in some earlier prezzies.
Yeah, if you thought, dude, this slide's great. If you add like Airy's failure to the slide, that goes through the complete historicity of how they lied about the ether up until now, and you can see like each one of these experiments was trying to measure motion, and when they didn't measure motion, they historically recontextualized it as failing to measure some form of ether. Right, so they did the same thing with Airy's failure. Oh, look, didn't detect deflection of starlight through the ether, therefore no ether. Earth's still moving, baby. Going on to like Nichols said earlier, they're like, all right, trying to detect Earth's orbital velocity, didn't. So that's a null. So the Earth isn't moving through static ether. Earth's still definitely moving, rocking, right? And then they go to Michelson, Gale, Pearson, and they're like, okay, we definitely got this rotational effect. It's definitely not the ether, even though it corresponds directly with the ether. Ooh, you know what it is? C plus V pertains in all frames, or however the relativists interpret Michelson, Gale, Pearson. I'm actually not sure how they reconcile that. Do you know what's their ridiculous explanation for Michelson, Pearson?
Oh, we're going to get into that towards the end here, but they're ridiculous. Right, cool. So there's actually not an official one, but they propose several scenarios in which it might be hypothetically possible. But there's no real definitive claim put forward, because again, if you're an inertial observer, should you be measuring the difference in the speed of light in your frame or not? We'll get into the philosophy of relativity to try and answer that one here. But so yeah, this is the classic equation that dictates all of these technologies and measurements here. So this is our delta Z. This is going to be our change in time. Our change in wavelength is going to be equal to the 4 times the rotation rate times the area of light that it has to travel. So I said that backwards, but the area times the rotational rate over the speed of light is going to give you the timing difference. So when this recombines, when this light beam completes its circuit and recombines, it's going to be out of phase, directly proportional to the area that it had to travel to complete this circuit and how fast this turntable was rotating. It's going to produce a pattern where the distance separated in between these fringes, separated in between these black spots here, is going to be proportional to how fast this was rotating. How crazy is that, lads?
Every time.
So which one is the one on the left is not moving?
No, the one on the, I have to go back to the paper. The one on the left is, okay, no. The one on the left is fixed to the rotor, like to the turntable, and the one on the right is the lab wall. So okay. as you see here, there's a harder Doppler shift here, in that at this midsection, and that's because it's from that receiver having to
a different inertial reference frame, not attached to the
mechanism. Exactly. So that is what is causing that deviation there. But the phase difference separation is the exact same. So what they showed is that the non-inertial observer on the turntable, even though he's in uniform motion and there's no relative motion between him and the source, but let's give it to the relativist, right? The non-inertial observer is measuring the same thing as the lab wall observer. That's illegal, guys. Party foul.
It was part of that rotation. It should only be detectable while within the rotation. I don't understand.
So what's happening here is there's a etheric mechanism perhaps that's facilitating this measurement. So what's happening here, right? Let's kind of break this down. As this turntable is rotating, the path length is actually changing as a function of the speed that it's turning, and the preservation of that path length, of like the total path length change, is what is allowing the speed of light, or is what is allowing the speed to be measured c plus or minus v, right? The v being going clockwise or counterclockwise, being velocity addition, or velocity subtraction going against, being the path length is being shorter if the mirror is moving towards it, and longer if the mirror is moving away. That's what this is describing. That's what's being measured. Now they say that this is only for rotation, because when you're rotating, right, you see this midpoint here at C on this rotor. This would be the center of this rotating turntable. So this is going to be where all motion outward is going to be relative to this midpoint in the center. So we know that there's a fixed midpoint here for this motion to be relative to on the outside. So there's no contention on absolute space for rotation. So that's why they say rotation is absolute. You could trace it right back to the midpoint here. Now for linear motion, they say no such midpoint exists, and there would be no way to preserve the path length change and the speed of light. We complete this circuit, and there would be no phase difference. This would measure basically all white lines. This would be these black lines would be real tiny, is what they would predict. But what actually measures in the linear case, so straight motion, and also the rotational, is a fringe pattern that's directly proportional to this. Because what was shown experimentally in 2004 by Ruyong Wang is that you could replace this area here that describes the circuit with length, which just describes the path length that it has to go for, like, linearly. So there's no difference here. So anyway, direct equivalence between this A and an L. You just change this omega to a V for velocity instead of omega for angular rotation. All right. So let's look at the results for these measurements. What does relativity predict versus what does the classic theory predict? In all cases, in all configurations, the classic theory, using the classic equation here, predicts the full fringe amount with no problem, because the classic theory is based on absolute space. In fact, you could use this ratio of over C to be as a constant. You could consider light having its own frame, and you're measuring motion against that frame in which light has a constant velocity. So it's inherent to the framework mathematically, it's implied philosophically, and through that, right? So the fringe pattern predicted, when you apply the math to that, actually makes the correct prediction down to the wavelength, which is the most precise form of measurement one could make. Relativity is off by a factor of 10 when taking the position of the observer fixed to the lab wall. This is irreconcilable.
Uh-oh.
Right? Like, this is good game, well played. You can't come back from this. You're fixed to a lab wall. Like, the only way to get out of this is to, like, not talk about it and or just, like, gaslight people. And we'll get into we'll get into the gaslighting, the mathematical gaslighting. While we're continuing the Prezi, try and think of a new term for gaslighting that applies explicitly for mathematics. You're mathlighting me?
Mathlighting.
Dude started mathlighting me. So anyway, we're going to see the mathlighting explanation that's given here. So what they conclude here is that the classic theory is in good agreement with experimental results, and the relativistic theory is contrary to the experimental measurement, and this can only be explained through relativity by invoking a fictitious reference frame at the midpoint here. Now, this will be important because, remember, relativity is supposed to be able to describe frames in relative motion without invoking fictitious frames. That's going to be a big part of the framework, which we're going to cover here in a second as we continue. But this was the only way that this can be explained is by saying we're going to move the observer from the lab wall. We got to move him off of here. And we're going to put him in the center here, and then he's going to watch another observer on the rim of this device, measuring the speed of light not being constant. And they do this through mathematical transformation. But if you notice here, there's no transformation here. This is just a direct ratio. How come this direct ratio against the absolute background describes the literal change in the speed of light that's measured by an observer without any transformations? Precarious.
So you're saying the relativistic theory is not holding water when it comes to this test?
Well, that's exactly what I'm saying. And in 1913, it didn't hold water when Sagnac did his experiment. And actually, this gentleman here, Mr. Paul Langevin, had to come in and give everyone the relativistic explanation, right? And first, well, we'll take a look at what he did as we continue. But remember this man's name here, Paul Langevin, because we're going to come back to him. So a quick recap on the 1913 experiment that falsified relativity theory. So before we get to that, let's do this backwards. Let's do relativity first, so we can understand what Sagnac falsified. So here we're looking at Einstein, 1905, that famous relativity paper on the electrodynamics of moving bodies. Right, this is a famous diss track that Einstein put out against the ether. Right, so he opens up strong right here in the first paragraph, page 1, and the first sentence on page 2, which ends from page 1. Right, let's contain the most important and pivotal pieces of information about the framework. So here he talks about the laws of mechanics and which frames they hold true in, which their definition is an inertial frame that's in uniform constant motion. So if you're on the Earth, you're moving around the sun at roughly 30 kilometers a second, you're not going to notice that velocity, right? All the laws of mechanics are going to hold good in your frame. If you're on a train that's moving at a constant velocity, right, you're not going to notice any change. So the laws of mechanics are going to apply. You would only be able to distinguish that frame through dynamic analysis, but that was a previous Prezi, right? For this, we're just taking their definition at face value. And then on top of that, where he says, where he's defining all inertial frames as one where the laws of mechanics hold good. So any frame where that's in uniform constant motion, we're good to go. This is where his theory is going to apply. And then on top of that, he says the speed of light is propagated independently of the motion of the source or the observer. And this is extremely important because what he's saying here to answer the Michelson-Morley experiment is he's saying that motion, like a linear motion when you're in constant motion, you can't use light to tell the difference, to tell a timing difference. It's not going to measure anything. You're going to get a null result, right? That's the explanation that's put forward because they didn't get a measurement that was to the magnitude that they needed to substantiate with the ratios that they were using for Kepler's laws and some Newtonian dynamics. But they just were, because their math worked out, they just assumed correctness and proceeded onward. So this theory is what's put forward and is the backbone of mainstream physics to keep the philosophy alive that the Earth is in motion. So anyway, with those two postulates, the constancy of the speed of light with respect to inertial observers, and in addition to that, he says the introduction of a luminiferous ether will prove to be superfluous inasmuch as the view developed here will not require any absolutely stationary space provided with special properties, nor assign a velocity vector to a point in empty space in which electromagnetic processes took place. Okay, so what is that? That's really important because he's removing the medium, right, as a physical medium, like the physicality of it. And he's also removing the mathematical concept of it, where when we go back to this equation, and I said we can consider this V over C, we're making this all motion relative to the light frame, so to speak. He's removing that concept. So now if you want to talk about light and motion, he says you have to use a Lorentz transformation. You have to use this equation here to describe it. You have to take the source, you have to take the detector, and you have to describe their timing and velocities based on in their change in timing or space and time with respect to their velocity using these equations, using the Lorentz transformation. So what this equation says is how fast you're moving is going to change your measuring rod, right? And it's also going to change your clock as a function of your velocity. And in addition to that, in addition to this equation, because he's removing the concept of an absolute background, absolute time, absolute space, we're deviating from this. He's redefining time as a function of velocity here. When he gets into the definition of simultaneity, this is where he's saying that time is a function of velocity, and then this is what the mathematical representation of what that looks like. So we got our time variable here. This is going to be defined by our beta. This is our gamma factor contraction. So this is going to be beta equals 1 over the square of 1 minus v squared over c squared. So this is going to be, you're going to put your velocity in here, and this is going to be how much your time coordinate is going to change. And the same with your distance coordinate. This is going to be your link contraction and time dilation. This is where these variables come from. They come from a change in your velocity. This is what these represents. And then so you would have your stationary observer and you would have your moving observer. Your moving observer is going to be link contracted, time dilated. Your stationary observer is going to be able to tell the difference, right? Because in the moving frame, you're contracted, you can't tell. But mathematically, you're measuring the relative distance or your change between these 2 points. Does that make sense?
So you're saying we have an elliptical orbit, right, around Earth, or
Mm-hmm.
around the sun, heliocentric model.
Mm-hmm.
So speeds are going to change. So are we all changing sizes and time is changing like throughout the year?
That is a fantastic question. The short answer to that is yes.
How much bigger am I getting?
Ooh. In an upcoming presentation, we'll go over the exact amounts. Dude, it's ridiculous. It's smaller than you would ever like. It's so funny that they hoodwinked us with this, and people think just because they carry some decimal places over 6 places that this is like, oh, dude, we've got something here.
But with sufficient math washing, anything is possible, Alan. You know this.
Dude, they math washed us. They math washed us and math lit us. Okay, so we've learned the basics of the framework and philosophy in math of relativity. There's one more important part about inertial observers and reference frames in regards to rotation, because we covered the linear variant here. Now, what does Einstein say about the circular variant here? So he gives the example of a clock going around the equator. So clock A is moving around clock A is stationary at the equator. Clock B completes an orbit or a circuit around the equator, returns, and it's going to be desynchronized by a factor of its velocity here, which is what he's saying. And he defines the application of his equations in this frame, because remember, if one frame, you're moving in a straight line, the other frame, you're going in a circle, you're accelerating, right? But he goes on to say here, it is apparent that if the results hold good, if the clock moves from A to B in any polygonal line, and also when points A and B coincide, so when the circuit's complete, in any polygon, it doesn't matter if it's a circle or if it makes a dodecahedron or a parallelogram, doesn't matter. Oops. I don't think dodecahedron was quite the right word there, but see, it doesn't matter. And then he says, if we assume that the results proved for any polygon line is also valid for any continuously curved line. So, quick question for the lads. A continuously curved line that has a point A and B that coincides is otherwise known as a
circle.
Oh, got it. Nailed it. Nailed it.
I notice he uses the word if a lot.
Well,
that's not very
this is based on a thought experiment involving a train.
And if the clock, okay, why not take a clock and move it? Actually move the clock, not say if I move this clock, but actually, did he ever try any of this?
Did Einstein ever do an experiment? No, but he did own a patent for a dress or something. Now,
with a blouse, it was a beautiful blouse.
Now, he is describing a light clock in these scenarios, and no such light clock existed at this time, but the clock that he was referring to exists now as an atomic clock. So all of these experiments that are said to confirm link contraction, time dilation, blah, 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 right, are now measured through deviations in atomic clock, which we can get in, which, whole separate Prezion, all of that. But at this time, nope. None of this was confirmed. And it's actually all based off of a thought experiment where he was the Einstein train thing, because all of this is prefaced on relativity of simultaneity. So the removal of absolute time, right, to get there, to get people to accept that, he used the train example, if you've ever heard that. But
yeah, I was just thinking of how, because I've had a couple pocket watches, some of them that don't, there is no battery in it, which what they would have been using back then. And it lost 27 seconds a day. Like every 24 hours, I would have to, every couple of days, I'd have to go and move it a couple minutes, because it's hard to find two watches that, count the exact same amount of time. I bet it's rare.
Absolutely. So let's do a quick recap on what we just learned mathematically. So what Einstein was talking about when he says, we're not going to assign imaginary vectors to electromagnetic processes. Remember how I talked about the change in path length on this apparatus is dictated by how fast it's rotating. So Einstein's saying that he can describe this with his equations by using the frame in which the source and the detector are located. Now, if you wanted to use a fictitious frame, which is what they end up having to do, you would apply this Lorentz transformation, right? You would hit up your boy Lorentz transformation, and you would take the coordinates here, starting with the midpoint of this apparatus. You would put a lad here, and then you would have the motion. All your link contraction and time dilation would be done by an observer fixed to the rim here, rotating relative to this fixed midpoint. So when you apply Einstein's equations to where both frames are fixed to the lab wall, it's off by a factor of 10. Makes the wrong prediction. So that's what's being described there, unless you transform to the midpoint, and then you could describe the full timing difference relative to this midpoint. And that's what they do. And that's an explicit violation of the theory, because remember, he says, we're not going to use an absolutely stationary space provided with special properties, nor assign velocity vectors to a point in empty space where electromagnetic processes took place. So so you can construct a fictitious mathematical overlay of this apparatus to describe this, but it would be a complete violation of the theory that's being put forward by Einstein, which is supposed to supersede this theory, which describes it on the face of it using a preferred frame. Right? When you hear a preferred frame, that's what they're talking about. A frame that all motion is relative to. So Einstein can't supersede this equation. His theory has to agree with this. You can't supersede the classical theory unless your theory agrees with what is already established, and then adds, things to it that, accounts for things that the classic theory doesn't. It's not backwards, right? We don't not account for the classic and then do whatever we want here. There's a specific order of operations here that's supposed to be followed. Someone's supposed to be in charge here, right? All right. So now that we're all caught up on the significance of what's put forward, we're going to look at what Sagnac did in 1913. So this is a polygon configuration here. This is the closed circuit of light here on a rotating turntable, where the source is fixed to the turntable and the detector is fixed to the rim. And this fringe pattern that gets measured is directly proportional to how fast this turntable is rotating. So if we do a Lorentz transformation here, or actually before we do that, let's analyze this turntable.
Now, does it ever, the fringe patterns, do they ever like overlap to where it would look normal again? Could you spin it so fast that like where the lines, you know, it says since it's time or speed dependent on how far the breakup is?
It's so interfered with that it magically goes back to where it started. Is that what you're saying?
I think you would have to spin it like way too fast. That would be it wouldn't be possible.
Light?
Yeah, it wouldn't be possible.
Okay.
But that would be interesting though. So let's see. We have a light source fixed to this turntable. We have a detector here. We have a fixed path link, right? It's not changing. When this is in rotation, does the path link between here and here change? No, there's no relative motion between them, and that's why Einstein, and one of the most coherent things he said was that, you know, this would be equivalent. If so, we have to move. You know, it has to apply logically, because if you, let's say you take the orbit of the Earth around the sun, or even suppose, let's just like assume globular dimensions and all that. Let's assume satellite around the equator. That orbit is so big, it might as well be linear. It might as well be straight. So he's saying, like, if you zoom in on any portion of this, it's going to be straight. So my equations have to apply here logically. So they're locked in. So Sagnat's like,
sense.
Yeah, so Sagnat's like, okay, cool. Let me see what happens when I put a light source on a turntable and see what happens there. Measures the full fringes. So that's a direct falsification of Einstein's predictions. Now, remember, Paul Langevin had to come in and fix this, and we were talking about what he had to propose to fix this. So relativity theory has already been established. We went over the rules and regulations, and we're going to see what this lad is doing here. So what he does for the first thing is he fixes lab time to the he basically uses lab time for the midpoint, and then that allows him to preserve the distance change. So he'll be able to describe the timing difference based on the distance change by essentially rotating the coordinate system around that midpoint. So that probably sounds, Alan, it sounds like he's using a fictitious midpoint. Yes, that's all he could do. We have a nice cylindrical Minkowski space-time coordinate system here, and at the center of that coordinate system is our fictitious midpoint.
Is that what Blitz tried to do? That looks very familiar. Is that the Blitz? Okay.
That all motion is going to be relative to. So we have here this theta d, right? This is going to be all distance radially outward from this radius, which at the center of the radius is defined by this time coordinate, which is going to be using lab time, which is he's basically using a fictitious reference frame to describe the speed of light going plus or minus the angular rotation rate, you know, going clockwise or counterclockwise with it. So that's his first proposal that he tries to answer with. The second one he does is a little more dubious. Here he changes lab time to be equal to the time in the rotating frame, which doesn't make any sense. And then he changes the distance path length that way by redefining time. And then you'll notice that it's still using a fictitious frame to do the same thing. He hasn't shown how there can be a first order timing separation in the speed of light going clockwise and counterclockwise to itself without using a fictitious frame. Because the thing with the Lorentz transformation, right? When we look at the actual equations that Einstein is telling us we have to use when we're talking about motion and light, we have to use these. Now this gamma factor, right? Link contraction and time dilation, the gamma factor they call it. This is extremely, extremely tiny. And if the velocity you're inputting is way less than the speed of light, it's going to be even less. Like, think about this, like the rotation rate of your turntable would be like, you know, 7 miles an hour squared, right? So 7 miles per hour squared over the speed of light squared. So like 300 kilometers a second squared. That's going to be ridiculously small.
Teeny tiny.
So what you're going to get out of that is not something that's able to even describe what's being measured here in these fringe patterns. Relativity would predict that this black line here would be like, you know, just think of it being way smaller than what it is now. Like so small you can barely see it. But yeah, we have this nice big gap here. Well, that gap's way too big for relativity. So they can only answer it by doing that fictitious frame stuff. And this is Paul Langevin, who came through to be the relativistic fixer, because nobody, especially Einstein, never answered the Sagnac effect. This guy was one of the first to try and do it. And this was the explanation that they went forward with for many years, what Paul Langevin put forward. And then in modern times, we have PhD Blitz, who tried to do the same thing when I was asking him about an answer for the Sagnac effect, how there's no relative motion between the source and detector, how you have to use a fictitious frame. He was like, no, you don't. Let me show you how to do it. Let me start off with the Minkowski rotating cylindrical coordinate system, which has a fictitious observer in the center, in the midpoint here, defined by the radius. Okay, cool. Then we're going to break that apart into a Cartesian coordinate system, which is like rectangular here, like, two-dimensional now. Still got our midpoint though. And then we're going to make all motion relative to that midpoint. We're going to drag the coordinate system around that midpoint to describe the timing difference. Does that sound familiar, guys? So there's no answer.
You don't need an observer. Hold on, let me just invent one, put an observer right in the middle via some Cartesian math, and then proclaim that you don't need the thing that I just did.
How is that different than what Einstein said not to do?
Yeah,
it's not. It's explicitly not. And the only way, like the way that they teach relativity, is so convoluted that the end result is the student doesn't even know that they're violating this. Like I've read this. Oops, I've gone over where's my Einstein stuff? Oh, right here. I've gone over this with PhDs, like the direct significance of this, just the first page of the theory. Right, about like what frames can we use? Like this page and this page specifically. And it's like, they're like, what? You can use any frame you want. Didn't you know? Like, no, didn't you know?
Yeah, didn't you know?
Didn't you know you can't do that? But no, they don't know. So that's the issue. Is like, if you're not taught the rules and you're just taught this theory has unlimited correctness and application. You
have unlimited correctness. Just go wild. Doesn't matter. Can't go wrong with it, okay? No matter what you can do with it, we can unfalsify it later.
Unlimited correctness, bro. All right, so we covered what Paul Langevin did. We covered what Blitz did. There's no actual answer to this without violating the postulates of the theory. And if you violate the postulates of the theory, your theory is invalid. Because postulates are just ingenious conjectures. They're not laws of nature or anything that's been observed or anything like that. It's just something some guy said. So conclusion of this, irrespective of the perceived constancy of the speed of light, a first order timing difference is measured with respect to the counter-propagating light beam going clockwise or counterclockwise to itself, which produces an interference pattern, which is directly proportional to the velocity that produced them, whether that be angular velocity or rectilinear velocity, just your everyday average velocity. The etheric framework mathematically is still used today, even by relativists, whom it is strictly forbidden. And we're going to go into some more examples of that. We're going to continue on. There's a couple more to add on after the conclusion here. Albeit they do it in creative ways, like redefining absolute time to be equal to the variance in time as a function of the rotational speed relative to the center.
Again, what they're not supposed to do, right?
Explicitly what they're forbidden to do by the sacred text of 1905 on the electrodynamics of moving bodies.
Wouldn't that be a preferred position?
Indubitably. That's exactly what it would be. The exact thing that Einstein
not if you
says.
don't call it that exactly, it turns out. If you just don't think about what it's called, you can use it indirectly, right?
And aren't we supposed to avoid that at all cost? The idea that we're in this preferred position.
Ooh.
We're special.
Yes.
What did Hubble think of Einstein? Did they get along?
Never met her.
They only invoke a special or privileged position when violating postulates of relativity. That's a nice thing to point out, dude. That's really funny. I haven't noticed that.
Dude. All right, so we went over relativity. Quick recap. No ether as a physical medium, because if you did, all motion would be relative to it. So we got to get rid of that. There can't be one, right? So at least what Einstein's proposing here is logically consistent with like the execution of it. Can't have ether because all motion, like, as a physical medium, because if you're in a medium, all motion is relative to the medium. All waves in that medium would be, you would be able to measure relative motion, through the timing difference created by that medium. So that's off the table here. So that's gone. And then also the mathematical concepts where we're using an absolutely stationary space or assigning special properties where we can assign imaginary vectors for electromagnetic propagation. We're not going to do any of that. We're going to redefine, there's no absolute time, there's no absolute space. We're redefining time as a function of velocity. And here's what the mathematical representation of that looks like when we got our coordinate system transformation for our time coordinate being equal to the gamma factor contraction minus the velocity times the distance over c squared. Lots of squarings of c here. And then our length contraction is going to be our gamma factor times the distance minus the velocity times time. And then here is the gamma factor the gamma factor correction, 1 over the square of 1 minus velocity squared over c squared. So just reiterating that time, well, not only time, but also distance is a function of the square of velocity over c squared. All right, then also the frames in which these equations apply to are also rotating frames if they're rotating in a uniform constant velocity. So this is important here. If one of the two synchronous clocks at A is moved at a closed curve with a constant velocity, it will return at its journey at A, lasting t seconds. Oh, no way. So if you're rotating at a constant velocity and you return to your original starting point, these equations apply, boys. Is what we just read. Now here, I've done some generous highlighting, as Shane would like to say. However, I would like
the bottom still. I don't know what she would do.
However, I would like to point out that all the important information starts at here and ends here. So was I wrong to highlight the whole thing? I don't know. If I'm wrong, I don't want to be right.
Highlight the title though. What's up top?
Anyway, we're going to describe what this means now and move on. Okay. So here we have a list of 21 citations that are trying to describe the Sagnac effect as a relativistic effect. If the Sagnac effect is a relativistic effect, guys, shouldn't there be maybe 1 or 2 ways to look at it, possibly 3? 21 different ways to try and do it. Why are all these people through all these years, right? This goes from 1917, 1918 to 2000, or no, I'm sorry, to 1994. Right? All in between here, people are trying to fit the Sagnac effect into relativity. Why are they trying to do that? Because some people have realized that it is not derivable as a relativistic effect. It's impossible. If the speed of light is constant and there's no way to preserve distance change, the circuit will be completed and there will be no fringe pattern produced. And that goes directly against experimental measurement. So the theory would be false. So these people are trying to fix it. Right?
Yeah, big money on fixing these.
If it can't be that it's false, it must be that you're wrong about it being false. That's the way to go.
Have you guys ever heard, go get your Nobel Prize? If relativity is false, go get your Nobel Prize. Guys, if you would like a Nobel Prize, show how relativity can derive the Sagnac effect.
Yeah,
these people were all trying to get that. I mean, that probably wasn't their primary motivation, but had they actually done it, they would have gotten it. So let's see. The important ones to note here are that they're all fictitious frames, and then it gets into some of them gets into the question where they're trying to answer. Shane asked earlier about Michelson-Gale-Pearson. Well, in one of these, here's the thing: if you're in a non-inertial frame, right? If you're in the frame that's moving, you're in the contracted frame, right? So you have to have the difference be measured by some other frame. So what they're doing for Michelson-Gale-Pearson for any experiment that involves the rotation of the ball, what they do is they put an observer at the center of the ball, and they say, "Hey, you guys on the rim of the ball, you guys are non-inertial observers because ball rotate, right? And although the ball rotates slow or whatever, right? Light notices, but you can't. But light notices. So, with respect to this fictitious midpoint, we can talk about that timing difference now. Now, here's the thing, lads. We're in the non-inertial frame too. We shouldn't be able to measure the length contraction and time dilation in our frame. We shouldn't be able to measure the full fringe pattern in our frame. We should measure no fringe. A lad at the center of the Earth would have to have his telescope aimed up at our apparatus, and he would see our friend. He would see us looking at the speed of light being the same, and then he would be like, look at those guys measuring the speed of light being the same. Don't they know that it's not the same?" So that gets into this whole debacle of yeah, we can answer it via transformation, but the question arises, should we even measure it? So here's 21 people trying to get to the bottom of this predicament. And then it says here in red, the classic kinematic derivation, which really is dynamic, because it's describing the path length changes relative to C as defined as as an inertial frame, as a fixed constant value to be relative to. So anyway, the classic dynamic derivation, as it has been used by many authors, see above, has the advantage of yielding the correct first order advantage, resulting in a very simple and intuitive way. So all of these authors, right, who were also trying to derive the Sagnac effect through relativistic means, also had to hit up your boy, classic derivation. That's
We
cool.
all had to use it.
Didn't you know relativity predicts everything and can't be wrong? So therefore, we can backwards derive a way to adapt what is a first order measurement using our math and coordinate system transforms. Everyone will be fooled.
Oh, that's super important. Let's talk about what a first order measurement is real quick and the difference here. Is this equation, this is a transformation. This gamma factor here, right, is a secondary term that's added to the actual velocity component and the actual distance component. I'm sorry, yeah, well, what would actually be the time component and the distance component, respectively, not the velocity. But right, so this is a secondary term. This is not describing the first order term. So the first order component of this equation would be velocity, right? We have this absolute magnitude, right? We have this velocity value. It's an absolute number. And we're going to, let's see here. What are we doing here?
You're in first order, second order?
First order, second order. Okay, right. So we got our velocity order here. Now, in this equation, thank you, sir. In this equation here, this is describing the first order timing difference based on the path length and the rotation rate, right? So that velocity, that first order effect, right? That absolute magnitude amount and the absolute starting path length, right? And that describes, when you ratio that against the speed of light as a constant, you get the ability to describe this dark fringe pattern here, how much of this will be here based on how fast this is rotating and how long light had to travel, right? That's what is being described here in the first order, right? Directly how fast this is rotating. Relativity, with that second order prediction, doesn't predict how fast this turntable is rotating is going to be how fast or how much fringe is produced here. Because it's a secondary term added to the equation, it predicts that this path length change is going to be extremely small, right? So small, in fact, that you could entirely neglect it. Because that's one of the ways that they try to do some algebraic shuffling to throw the gamma factor into the classical derivation. Because here's what you'll find if you start looking into this. You'll find like the Tartaglia paper in 2014, where they tried to add an explanation to Ruyong Wong's experiment. So just imagine that beta that was written on Einstein's paper here, this beta, right? Just imagine this little beta here next to this. And they're like, look, relativity predicts this, guys.
It all works now.
But here's the thing. When you work that out algebraically, yeah, sure, that term is definitely in there. He added the term. But when you work it out, all that, the part that describes this portion of it, that's what's measured, is described by this part of the equation, right? The gamma term is completely neglected. You wouldn't be able to measure it. It's not
so infinitely
nonsensical horseshit.
You couldn't account for it if you wanted to.
So I'm not really getting bigger and smaller.
It's smaller than it's smaller than the wavelengths that are making the measurement, bro. It's physically impossible.
If math became reality, this would be a tough one.
That's so crazy. Think about that. It's mathematically impossible for them to predict the first order fringe. That's why 21 lads over the course of 60 years were like, hey, anyone want to take a crack at no? Nothing? Guess what? Guess we'll go back to the classic. Guess we'll go back to this real quick. Why did they go back to the
So
classic?
it's all on paper. No actual test shows anything of what Einstein proclaimed.
Not in interferometry regarding speeds that are less than the speed of light, way less. You wouldn't possibly be able to verify it, and it wouldn't possibly be able to predict it unless you use a fictitious frame, which is why they do that. And then so this was actually noted, this whole debacle was actually noted by a man named Post in 1967 on the Sagnac effect. And he talks about the consistency of relativity, and the mathematical implications, because he was trying to add his own. He's one of the lads in this list here. Our boy Post, he's in here somewhere, one of these citations. And because what he proposed was preposterous, but we'll cover that in a second. But what he says here, to call it out on the face of it while trying to assert his own thing to fix it. Because see, that's the thing. Sometimes they'll call it out, but only if they're going to try and propose a fix for it. Because they're like, I want to be the new daddy. Daddy was wrong, but
submit my resume or whatever.
He did, exactly. So he's submitting his resume here. So to be consistent with the principle of relativity, which is that the constancy of speed of light and the all inertial frames are equally valid. So the inertial frames in this situation would be the light source and the detector, which are at a fixed point. There's no relative motion between them as they rotate on the apparatus. one has to demand that the Sagnac interferometer and the ring laser, shout out to Bob, cannot lead to a fringe or a beat frequency if the equipment is in uniform translational motion. And uniform translational motion can be defined by being in rotation at a fixed constant speed, right? It could, because like as we went over earlier, you can zoom in on any fixed point of that and it's linear, right? How many radians do I have to deviate before I'm rotating, before there's a fixed point relative to my motion? How many radians, guys?
I do not know.
No one does. There's no answer for that. It's nonsensical. How much of a turn do I have? Like, if I'm walking straight and then I start to deviate, like how much of the deviation is it going to complete an arc? Is it going to be like, now my motion's measurable because I'm relative to a midpoint that is completed by my arc of deviation relative to my linear path?
Sometimes when you don't know, it means you're not retarded. Yeah.
So here we have Neil Ashby, who went on like a 10, 20-year campaign promoting promoting the Sagnac effect as proof of relativity and being used in GPS as confirmation of relativity. That sounds pretty damning, right? I think we just disproved classical mechanics, boys, and we all should become relativists. What do you say?
Pass.
Well,
right.
They created the whole ECI frame to negate the Sagnac effect east-west. I mean, it's pretty funny. He's like, look, in this frame, you don't even notice it. You know what I'm saying?
Look, in this frame where the stars don't, or where the Earth doesn't rotate for 6 months, and
You don't say.
you don't even notice.
Okay.
Oh man. All right, dude. So we got relativity in the global positioning system, the old GIPS, I call it. So this is Neil Ashby in 2002. This is a couple years into his tour here. Observers in the non-rotating ECI inertial frame would not see the Sagnac effect. Instead, they would see the receivers are moving while the signal is propagating. Oh, no way.
How do you know what something in a fictitious frame that you invented would see? That's the silliest proposition ever.
So this gets into the debacle that I would laid out earlier, where they're not exactly sure if on the surface of the Earth we should be measuring a deviation, being in the frame that's experiencing the link contraction and the dilating. But he says, so he's laying out here that it would only be measurable in those frames. So he actually just conceded that this is not a relativistic effect. We're measuring on the surface of the Earth the variance in the speed of light, guys. In his opener, he conceded our point. Because you can't fix this without fictitious frames.
But I'm confused because it's framed under a title that says relativity in the global positioning system. So it would imply that like relativity is essential for GPS to work. Yet the second sentence says actually it works completely not because.
Dude, conceded the whole thing in one sentence or two sentences.
Man.
Observers in the non-rotating fictitious frame that we invented would not see the Sagnac effect. Instead, they would see the receivers moving on the Earth, in rotation around them at their midpoint. We're moving while the signal is propagating, measuring the speed of light not being the same. So if you're on the Earth, you're not going to measure the Sagnac effect. You need to be in the fictitious frame.
I think what this should say is, we fixed it. Behold, the ECI frame fixes relativity in GPS. We nailed it, guys. That's kind of what it says anyway.
Dude, and I just want to point out this, actually, never mind. We'll just continue on. But yeah, this Neil guy, he's a guy.
Quite a lad.
Quite a lad. All right, so we have Professor Carol Alley, who did a famous follow-up experiment to the Heffel and Keating experiment, where they did the atomic clocks around the world and found time dilation, except they didn't find it in the reciprocal clock that was stationary the whole time, which is mandatory if relativity is true. Otherwise, all they showed was that a clock in relative motion experiences desynchronization, which is also a classic theory prediction. So again, relativity scoots by with some mathematical finesse and no actual substantial experiment to back up any of the mathematics that's asserted with it, because along with the Lorentz transformation, the thing I didn't cover, but I'll cover real quick, is that the frames that you're defining have to be reciprocal, meaning the link contraction and time dilation experienced in one has to be able to be shown in the other frame. So if you can't show that physically, then it has no meaning, but you can do it mathematically, and that's part of that's part of what they like about the theory, is showing that reciprocal nature. But they only show it mathematically. So if they were taking measurements with a clock and moving it around the world, completing a circuit, and only the moving clock was desynchronized, but they were doing their relativistic comparison to the moving clock and the stationary clock would have to somehow manifest actual measurements that correspond to the motion of that relative clock. And that's never once been measured ever. And I bet you're thinking, Alan, that sounds ridiculous. Why would that be Why would that be a requirement? Well, it's because it has to satisfy Lorentz symmetry. It's part of the framework. But more importantly, it's mandatory for them, not us, because that's crazy. So anyway, this lad did a follow-up experiment and got said, hey, my clock desynchronized in agreement with Einstein's theory, blah, 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 right? So he's in 1979, he's like, hey, relativity is no longer just a theory of math for the lads in astronomy class. We're bringing this to the realm of engineering. It's now a necessity to account for relativistic effects of time dilation to be accurate in GPS. Okay. So 17 years later, let's see what old Carol Alley has to say in an engineering overview where they explicitly, GPS has been out for a while now in 1995, and they've got it's working off of classical equations, and all the engineers are wondering, hey, when are we going to put relativity in GPS? Like, Carol Alley 17 years ago said that it was here. We're just wondering. So anyway, Carol says at the end of this overview, there's a note from him where he wrote in, says, I would like to make another point. When one looks at differential GPS, the corrections that need to be made primarily the difference between the radial distance and the ephemeris and the timing readings on the satellite. And I believe this comes in because of the mix-up or aliasing, if you will, between these two quantities in the iteration produced that the Kalman filter is following. Okay. And if one perhaps does the explicit recognition of the special relativistic effects, and I mean, it took a long time to get the general relativity down properly, but I think it would be more or less correct now. So what they're talking about here that they were going over in the overview was that they need to make GPS more accurate, but they don't know how to do it. And the current relativistic calculations that they had for general and special relativity were so small that they basically canceled each other out and they could ignore them. And so they go over in this overview, they're bringing the authors bringing up the contentions of the engineers. And he's like, look, guys, even if we did implement it, tomato, tomato, right? We'll figure it out. And this guy, Carol Alley, is saying, hey, we've been working on trying to narrow down these corrections, that we're calling general relativity. And it seems to make it more accurate, but like, it's not implemented in the system yet. Like, what are we doing here? And remember, this is 17 years later from where it's now a necessity in the realm of engineering. And then he goes on to say the most damning thing of all, because GPS is supposed to be the backbone. Relativity is supposed to be the backbone of GPS, right? But it's the absence of the explicit acknowledgement of the special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity, which we talked about earlier, where speed redefines time and distance, and the associated Lorentz transformation physics, so the mathematical framework that we went over that Einstein says you have to use when you're talking about motion and light. There's nothing of that modeled in the current system, and I think there should be. Oh no!
It has to be in there for this to work. To 17 years later, him complaining that it's still not in there, but working.
That it's still not in there. That Lorentz physics, that these transformations do not exist. There's so as a consequence of what Einstein proposes, constancy of C, and relativity of simultaneity, which, there's no absolute time or space. And as a consequence of that, we have to use these equations.
It's like the arbitrary nonsense that you added on to Mathmagic your way into your philosophy. It's almost exactly like that. That's what it appears to be.
Exactly. And then all they have here is the, what am I looking for? Yeah. And then, so what they're all using is this. And actually, which we're not going to get into, but I'll briefly cover, the effect under general relativity and the effect under special relativity that they say that they account for, that they swear that they promise they account for, guys. You can actually derive those as a function of the Sagnac effect, and the way that it deviates from the relativistic prediction by like 0.0000000003 or something. So it's like practically indistinguishable for all intents and purposes. So like the mutual exclusivity between these effects is non-existent, because the way that they have it broken down, right? You would think like, oh, this is a general relativity effect. This is a special relativity effect. Does that mean it's going to look differently in the measurement? No, the equations predict the exact same type of change. So what would in other words, if you were to say, we're going to analyze this fringe pattern using general relativity versus we're going to analyze this fringe pattern using special relativity, which one would be using gravitational potential as a warping of space-time, and the other one would be using velocity changing space-time. It's not going to change. This measurement's not going to look any different no matter which framework you use to kind of put that into perspective, because they have it broken down categorically. Like these are two, like they're like as if it's going to be manifested differently maybe, but you can more easily think about it as like they're just going to be adding on a little width to this black part, and then they're going to be adding on a little more for special relativity. And although they have it categorized differently, it's not going to be like there's not going to be like a separate effect like, oh, there's now a mid fringe pattern in between these or something like that. You know what I mean? It's all the same. It's all going to manifest in the same way. They're just saying that the change is going to be ever so slightly more than what than what it looks like now. But because it's so small, you wouldn't tell the difference anyway. So it's all the same. Isn't that awesome?
Like, is that possible to test? Like, could you speed it up to like 33,000 RPMs and maybe, could they in any way, shape, or form like show this little tiny thing we're supposed to see?
No. Remember, what they actually predict is so much smaller than what the velocity is, even the level of the velocity that's even causing it. You would have to be, I mean, no. No. All right.
Teeny tiny infinitesimal numbers, like 10 to the negative 17 torr type numbers, right?
Yeah.
Lots of zeros after the decimal point.
Even smaller.
Wow.
And then so from that engineering overview, this is where he talks about, as we have shown, you see whenever the math for the general and special predictions, introducing the gamma factor makes only a change of 2 millimeters to the classical result. In short, there are no missing relativity terms. They cancel out.
Oh, isn't that convenient?
Cancels out in the Sagnac, and the linear Sagnac effect cancels out in GPS. In the most extreme case with the like if we took their velocities at face value, right, and we didn't introduce any sort of scale invariance to make it more palatable or whatever, if we took it at face value, their relativistic effects are completely negligible. And then real quick to end off on Neil Ashby's documentation where he was talking about transformations between the ECI and ECF reference frame. Well, he's actually using a Galilean transformation here between the two, which is absolute time and space. So even in their fictitious framework, they're not even doing that. They're not even transforming the timing difference correctly from that either. Why, you ask? Because the gamma factor is too small to ever matter in any circumstance. So what did Bob measure exactly with 15 degrees per hour? What does a Sagnac interferometer measure? What is anytime they talk about ball rotating or measurement of the ball rotating or thanking Bob, they're actually talking about the falsification of Einstein's theory. They're actually saying, hey, thanks for showing that the Earth is stationary with respect to the rotation of the sky, which is most likely translating an ether wind down to us that's being measured, which is why we can measure sidereal fluctuations through using the speed of light when it's in the east and west orientation with respect to north and south.
Yep. Thanks, Bob, for measuring a non-exclusive ether rotation that cannot be a uniform rotating sphere in any which way. Excellent.
Oh, man, that's so awesome. But yeah, mainstream paradigm, quick recap. Mainstream paradigm has no way to even thank Bob. So the whole, like, thank Bob, thanks Bob has to be, that's where like the op around it has to be so big. Like Flat Earther disproved their own theory by measuring ball rotate. It's like just that device making a measurement shows that the Earth is stationary and non-rotating. Once you work out the implication of the measurement and how it's produced, and then you go through the history of all the other measurements that were supposed to substantiate Earth's velocity, etc. None of this works on. They all measure the rotation of the rotation of the sky.
Yep, they all match sidereal rotation. They all fluctuate in accordance with sidereal motion. They all take into account a moving sky and a stationary Earth. That's just the way it is.
It's the way it be.
That was an awesome Prezi there, Alan. I learned quite a bit on that one.
Thank you, sir. The Sagnac effect is one of my favorite subjects, man. It was by far the most intimidating when I started looking into relativity and whatnot because of the whole thing. Like Flat Earther measured the rotation of the ball. It's like, oh, shoot, what happened here? And it's like, what happened here was one of the most scientific, a scientific cover up, right? There was a big car train accident, right? And they covered it up with math, and they were like, "Don't look here, guys."
The cover-ups are the best to look into. Matter of fact, all the experiments about ether are specifically the most lied about experiments ever. Whenever they get a result that doesn't align with it, they just recontextualize it. Like, oh, that's not what he was looking for. Said who? Well, the guy 200 years later who found his result inconvenient. Oh, okay. Well, I'm going to read what the dude who was doing the test said and what he was looking for, and we'll go from there. All of these experiments are the most lied about ever. So when they get into like the history and the contextualization, it's so funny when they just cover it up with math. Those are the ones you want to look into.
Yeah, one of the favorite explanations is like the way that they'll try to segue it in is like, well, we know the Earth is in motion, and these guys were trying to test it, and because they didn't get the value of the thing that we know, then what they were doing is wrong.
Isn't
It's
that a
like-
crazy way to
it's
look
like-
at it?
it's like,
no,
what?
no.
Hold
Someone
on,
did that to me
what?
on Twitter. It's like, here's an experiment they were testing for the motion. It's like, no. They knew the motion. They were just testing for the thing they didn't find.
What? It's like motion. You know, you can test for that sort of thing, right? They're like, no, you can only test for ether, and they've never found any.
That's
shoot.
what it is. That's what it turned into.
Every experiment ever has tried to find ether. They can never do it. It's like, shoot.
They all failed. Everyone.
That's so fun. That's exactly what it is. That's what happened. That's how they frame it.
It's awesome.
Good
All right,
stuff.
let's see here. Let me see here. What do we got going on in chat? We have Liz the Iron Maiden, treats for Hank and Minion.
Oh, thank you, Liz. Those are Cammy and I's dogs. We'll
Nice.
see. I don't know. They're such jerks, man, to guys. Like, they loved Liz. Not a bark, not a peep, nothing. But Jaren will have a buddy come from Denver and stay, for a couple weeks or something. And he pets them, they've met him multiple times, but every time he walks out of a room, they have to like charge him and the hair stands up on their backs and rah, rah, rah. But it's not just him. It's like every guy that comes into the house that isn't me or Jaren. They're just retarded. And I don't know how to break them of it.
Yeah. Sadly,
more house
sadly,
parties.
you never will, and you should lean into it.
Get them. Yeah.
Yeah. You should be like, you keep doing that. Good boy.
Well, no, I like it when they do it, to somebody who's not supposed to be in the house. But once we introduce them and say, hey, they're okay now.
Nah, let them know they're constantly being watched. Eyes on you at all times. To establish dominance.
Yeah, I'll let them know that you're on their side.
Yeah, thank you so much, Liz. Much appreciated. All right. Shane, what do you got coming up this week, sir? Actually, wait. Zach, what do you got coming up this week, sir? Let's do you first.
Yeah, we're going to be doing the same old Monday, Wednesday, Friday Ironworks. Thursday, we'll be doing Glowbusters Tech on water. We started part 1 last week. Just water is pretty amazing. It's the weirdest element that I've heard of. Like, the more you research into it, the more you realize that you don't know what water is. Nobody knows what it is. We can't make it. It's everywhere. And yeah, it's pretty fascinating when you start deep diving into, like, when it heats up, it expands. When it gets cold, it expands. It's just weird, dude. It's like a very weird element when it comes down to it.
The only thing I know about water is that it came from a comet that hit the Earth and then melted, and it gave us all the liquid that we needed for the primordial soup to begin. That's all I know.
And the fish monkeys came from there, who obviously were our grandparents. So
Okay, I'm not going to finish it, but that's one of my favorite South Park ones ever. I've showed that to so many people. It's like a 42-second clip of Mr. Garrickson explaining evolution. If you haven't seen it,
it's not
you
far
need to
off
laugh.
from a hard steel man of their actual position.
No, it's not. That's the genius of it. Yeah. Oh man, they were so good. Making fun of something while like promoting. I don't know. They're just geniuses, comedic geniuses.
Social commentary.
And without, they never picked any side. Everybody's on the table. There is no religion. There is no, ethnicity, nothing. Everybody's up for grabs. You do something stupid, they're going to make fun of you, no matter what. That's what I loved about them. Now I haven't watched South Park in years, ever since they started doing it in sequence and, keeping track of what happened last week and yada, yada, yada. It's like, no. They lost me.
All right, what do you got coming up this week, Shane?
Nothing. We're doing Bennett this week. I think he's taking our Tuesday slot, right? Or not? With the Einstein train. Yep.
Yes, there's going to be an update to the Einstein Train Challenge and Newton's Bucket, I think, and then there'll be a live Q&A after. So if you guys have any questions about the ether framework, relativity theory, or whatever questions you have, the Hildegard model, the alpha model, come by our chat on Tuesday, 8 p.m. Bennett will be doing a presentation and then Q&A after. And then Friday, of course, will be community Twitter space night. We'll be hanging out on Twitter and seeing what the lads are up to over there. And then Sunday, Shane will be going over his Prezi on the old say the word for me. I can't do it. Chronomancer.
Yeah, the eclipse. Can we
retitle it a chronomancer? Can you be
Yes.
some sort of chronomancy?
Only if I had a cape, I think. Right? You need a cape to be a chronomancer.
I
Great
mean,
video game back in the day, Chrono Trigger.
Oh
Did
yeah.
you guys ever play that one?
Oh,
Super
yeah.
Nintendo?
I've heard of it. It's pretty dope.
Loved that game. There was no Secret of Mana.
Oh, secret. Okay, Zach, we're gonna have to talk later, dog. I didn't know you were a secret of mana.
Oh,
Okay.
dude.
All right,
Best
all
video
right.
game that started RPG video games, in my opinion.
Oh,
That's the one that
snap.
started it off.
I see you're a man of culture, Zach.
Oh yeah.
That's what's up. All right, so yeah, check us out later on in the week, and we shall return, lads and ladettes. Oh, and I think there's a, what are we doing? Oh, I thought there was something else.